Back in episode 19, we talked about how massive stars end their lives when they run out of fuel, leaving a core of iron. The iron core, unable to produce enough energy to withstand its own gravity, collapses so tightly that the electrons and protons within it merge to form neutrons, which arrange themselves into a sphere at the center of the star. The energy liberated by this collapse is so intense that the star blows itself to smithereens in a Type II supernova. Now that explosion is pretty spectacular. We've talked about that before. And it's also the forge in which most of the atoms in our everyday experience are formed. But let's not think about the explosion. Let's think about that ball of neutrons. What happens to that? Sometimes that explosion is so violent that the ball of neutrons just doesn't survive. It gets converted into another object, which we'll talk about in a different episode. But often enough, the ball of neutrons rides through the storm of the explosion and comes out the other end as a stable and very interesting object that we call a neutron star. Now remember that neutrons are fermions. They obey the Pauli exclusion principle, which means that they can't be in the same system and also be in the same state. They're all going to have to be at different energy levels, which means that the neutrons in that ball are going to have to arrange themselves into shells of energy levels, just the way the electrons within atoms do. The more neutrons there are, the more energy levels are required to hold them. The higher the energy level of the neutron, the more momentum that neutron carries. That momentum creates a pressure which pushes back against the gravity of the neutron star. That pressure is called degeneracy pressure. And what a pressure that is! A typical neutron star has about 2 solar masses, but it's only about 6 miles in diameter. And that means it has the density of an atomic nucleus, or about a quadrillion times the density of water. And that mass and density combines to give it a surface gravity. Wow, a pint would weigh 100 billion pounds on its surface. So this is a pretty interesting object, but it gets better. In general, stars spin, and the parent of the neutron star was probably spinning too, but then the core collapsed by a factor of 10,000, so like a skater pulling in her arms, that core spun up to a rate of, 60 revolutions per second. So now we've got this object that's 6 miles in diameter. It weighs twice what the sun does. It's spinning at 3,600 RPM, which is as fast as your hard disk spins. You think there's some kinetic energy in this thing? Oh, but it gets better. Remember, that parent star had a magnetic field, and when the core collapsed, it took most of that magnetic field with it and compressed it down by a factor of 10,000 or so. So at the surface of the neutron star, there's a magnetic field that's maybe 1 trillion times stronger than the Earth's magnetic field. That's strong enough to rip most materials apart. So now let's think about this for a minute. Here's an object with a truly radical magnetic field spinning at 3,600 RPM. What do you get when you spin a magnetic field? You get an electric field, a voltage, and in this case it's a big whopping voltage. So here's that neutron star spinning at 3,600 RPM, right? With this great big magnetic field rotating around like crazy, creating this great big electric field, this really high voltage. And that high voltage will take electrons and try and accelerate them. But there's this big magnetic field here. And when you've got electrons trying to move through a magnetic field, what do? Well, they rotate around the field lines like crazy. And what do electrons do when they rotate? They throw off photons. So there's these beams of light roaring out of the poles of this star. Now, it just so happens that the magnetic poles and the rotational poles of the neutron star don't often align, which means that these two beams of light swing around like some kind of crazy lighthouse. If the Earth happens to be in the path of those beams, then we see the lighthouse flashing or pulsing. We call that a pulsating star or a pulsar. Now, it takes a lot of energy to haul a big stellar magnetic field around and radiate those beams of light out there. And that energy comes from the kinetic energy of the neutron star's rotation. So as it radiates all that energy away, that rotation slows down. And as it slows down, the electric field gets weaker and the electrons oscillate more slowly, and the beams of light shift their frequency from high-intensity visible light down to radio frequency. But we can still see them, it's just that we see them flashing away in radio light, not in visible light. In fact, almost all the pulsars we know are in fact radio pulsars. The very first one discovered and the hundreds of the other ones out there, they're radio pulsars. Visible pulsars don't last long because it takes a lot of energy to emit visible light. So a visible pulsar burns through all that kinetic energy really fast and becomes a radio pulsar. Still, there is one visible pulsar, a very famous one, in the Crab Nebula, which is in the constellation of Taurus. This nebula is 6,000 light years away, and it's the remnant of a Type II supernova that blew up on July 4th, 1054 AD. The Europeans didn't say anything about it. They were in the middle of the Dark Ages. But the Chinese saw it, and they reported it. What they said was that it was visible in the daytime for 2 months, and they could see it at nighttime for full 2 years. When we look there now, what we see is a radio pulsar right in the middle of the crab, and it's flashing away 30 times a second. And if we take our best telescopes and we peer down the center of that, we see a flashing light in sync with the radio pulses. Overall, we know of several thousand pulsars scattered around the sky. Some of them spin at the leisurely rate of 1 or 2 RPM. Others spin at the crazy rate of 1,000 times a second. The consistency of their pulses is so regular that we use them to set our atomic clocks.